So this next topic we're going to talk about is molecular polarity. And it's a pretty important topic, as I'll show you here. So for example, let's compare water, H2O, and methane, CH4. And both of these have very similar molar masses. So for water, if you add up two H's and an O on the periodic table, you get 18.02 grams per mole. If you add up a carbon and four hydrogens on the periodic table, 16.05 grams per mole. So almost the same number. They have similar geometries. Electron pair geometry is tetrahedral in both, although water is bent molecular geometry. CH4, that doesn't have any lone pairs, would also have tetrahedral molecular geometries. But goodness, look at the difference in boiling points. The boiling point for water, if you tried to boil water on a stove, 100 Celsius, 212 Fahrenheit, all right? Methane, which is natural gas, by the way, more or less, minus 161 Celsius. So why would something in a similar electronic environment with about the same mass have such different boiling points? I mean, it's just crazy. The difference between those is like 260 degrees. It's just a crazy, crazy difference. And another thing, why is water so good about dissolving ionic compounds? Like if you put sodium chloride in water, the sodium chloride goes away. It becomes sodium ions and chloride ions. Why is water so good about dissolving these ionic compounds? And both of these answers come from what's called molecular polarity, which is a really important consideration in chemistry. And it affects things not only a lot in Chem 221 through Chem 223, but all the way through biochemistry and beyond.
When the balloon is rubbed with wool, the wool imparts a static electric charge to the balloon. When we place the balloon near the water, the stream is attracted to the balloon. The polar water molecules act as though they have an electric charge as well. Water molecules carry no overall electric charge, but they do exhibit polarity. The positively charged end of the water molecules and the negatively charged balloon attract each other.
This is kind of a fun thing to do if you have small kids. You can rub a balloon with a piece of fur and it creates a little bit of a charge. And if you have a very, very thin stream of water going down, you can actually bend the water to the balloon, which is kind of a cool thing. And this is a fantastic phenomenon that's only possible because water is very polar. And if you look on the right-hand side there with a little animation, you can see how the HOH is kind of like a V. Now we know that the HOH is kind of a V because water is in a tetrahedral electron pair geometry environment, and the HOH angle is bent, but the tetrahedron makes the HOH angle about 109 degrees. Water has, as we saw earlier, two lone pairs on it. So those lone pairs are centers of negative energy, and negative energy will attract to positive things and repulse other negative things. On the other hand, the two hydrogens here, they're going to be slightly positive. They're going to attract negative things and be repulsed by positive things. So on this right-hand animation, you can see how all the water molecules, they kind of orient themselves so the H's are closest to the negative balloon. And the oxygens are getting as far away as they can from the balloon because that's where the negative side is. So the molecule of water itself is polar. The molecule has a slightly negative side, which is the oxygen, and it has a slight positive side, which is the hydrogens. And this is an example of molecular polarity. It's not just a bond polarity, like OH would be a polar bond. The whole molecule has a slightly positive and a slightly negative side. And this is an important consideration when it comes to reactivity. So a molecule will be polar if you have polar bonds, i.e. they're made of different things, and you have to have an asymmetric or a molecule which is not symmetric orientation. So let's look at some examples. All of these examples have a symmetric orientation of atoms around the central atom. And what that means is that everything is the same. So on the first one, this would be an example of like beryllium difluoride. The beryllium would be the gray in the middle, and the fluorines would be on the outside. So around the beryllium, you have nothing but fluorines. That would be a symmetric environment, all right? There's no lone pairs. Everything is the same fluorine around it. Good to go. Boron trifluoride, BF3, would be another example. Everything around that boron is the same, all fluorines. Like you don't have two fluorines and a chlorine, or a hydrogen and two iodines. Everything is fluorine, so that would be symmetric. This is an example of a tetrahedral symmetric molecule, CF4. Everything around the carbon would be the same. You could also have CH4 or C-bromine 4. I mean, anything where the molecule is surrounded by the same kind of things, that's cool. And lone pairs count here, so no lone pairs, blah, blah, blah. PF5 would be 5 fluorines around the central atom for trigonal bipyramid. Sulfur hexafluoride, SF6, would be an example of an octahedral that was symmetric. So if you have a symmetric molecule, that molecule will be non-polar. It doesn't have the polarity we're going to talk about. But you can probably imagine that there's a lot of examples where things will be polar. Like you'll have, for example, in SF6, one of the F's will be replaced by a chlorine, or it'll be replaced by an oxygen or whatever. It breaks the symmetry. That makes the molecule polar. So if you have to guess, I tell people sometimes guess polar because there's a lot more of them that are polar than non-polar. However, it's better to kind of think about it and stuff. And we'll go through some examples here of how this works. So let's compare carbon dioxide and water. Which one of these is polar? And the best thing to do, draw the Lewis structures. So carbon dioxide is a carbon in the middle of two oxygens with double bonds. I'm not showing the lone pairs here, but they would be two lone pairs on each oxygen. Water, on the other hand, as we've seen, has a bent molecular geometry and two lone pairs on it. So around the carbon in CO2, we have just double bond oxygens. That's a symmetric molecule. So the molecule is nonpolar. Now, each carbon-oxygen bond is polar. Oxygen pulls a lot more. It has a bigger electronegativity than carbon. However, the pull to the right is canceled by the pull to the left, if you will. So the overall molecule is nonpolar. So you can have polar bonds, but a nonpolar molecule. But you don't see that with water because those angles are 109 and the angles don't cancel out. Like with CO2, it was 180. With water, you have 109-degree angles. So the oxygen-hydrogen bonds, each of which are polar, they don't cancel. If you've done anything with vectors in math, each of those OH bonds is like a vector, like a dipole, and you can add the vectors together to see if they cancel. And with 109-degree angles, they don't cancel. Now, if you don't know what a vector is, don't lose any sleep about it. You don't need to know about that, but that's really what's happening here. If the important thing here is that everything around that water is not the same because you've got two lone pairs, and lone pairs are different than hydrogens. So everything around the oxygen is different. This is going to be a polar molecule. Now, this is the measurement of the polarity, 1.85 dBi. That's what the capital D stands for. You don't need to worry about that. You can actually measure the polarity around water. It's pretty strong. CO2 would not have a dipole moment. There's nothing to measure. It would have a 0 dBi measurement, if that's where you want to talk about. All three of these molecules have a central atom and three atoms around the central atom, or AB3. So BF3, Cl2, CO, and NH3. So in boron trifluoride, boron would be the A, the central atom, and the three fluorines would be the three Bs. In Cl2CO, the carbon is central, and it has two chlorines and an oxygen around it. And with nitrogen and with ammonia on the far right, nitrogen would be the central atom A, and each B atom would be one of the hydrogens. So again, if you want to see if they're polar or nonpolar, do a Lewis structure. So boron trifluoride has boron with just fluorines around it. Each boron fluorine is very, very polar as a bond, but because everything is the same, it all cancels out. BF3 is nonpolar. And again, you don't need vectors to figure that out. You just need to see that that boron has nothing but fluorines around it. No hydrogens, no lone pairs, no oxygens, whatever. Just fluorines. That makes it a symmetric environment. Symmetric things, nonpolar. Now, Cl2CO, though, does not have a symmetric environment. It has a carbon-oxygen double bond and 2 carbon-chlorine bonds. So that molecule doesn't have anything the same. C double bond O will have a different polarity than CCl will, so nothing's going to cancel. That's a polar molecule. And ammonia, NH3, at first looks like it might be symmetric until you draw this Lewis structure. There's a lone pair on that nitrogen, and lone pairs are enough to break the symmetry. So around that nitrogen in NH3, you have 3 hydrogens and a lone pair. That also is not symmetric. Lone pairs break the symmetry too. That's going to be a polar molecule. So again, more often than not, guessing polar is probably okay. But again, be careful, because some things like BF3 will be nonpolar. So here's the kind of question you might see. It says, which of the following molecules is polar? All right. And maybe none of them are polar. It's hard to say. But anyway, the best answer here would be to draw out a Lewis structure for all 3 of them. So for example, boron and boron trichloride, that's a trigonal planar. Carbon and carbon dioxide, that's a linear electron pair geometry. Nitrogen N2 would be 2 nitrogen atoms together, and ClF would be a chlorine connected to the fluorine. However, even without drawing the Lewis structures, Cl and F, those are 2 different atoms, and they're connected to each other. Fluorine is the most electronegative, like we said, chlorine is less, so there's going to definitely be a polar molecule there because fluorine pulls differently than Cl. Now, if there's 2 nitrogens like N2, they will cancel each other out because nitrogen pulls, but they pull equal and opposite. That's going to be nonpolar. And we've seen how carbon dioxide is nonpolar. 2 double bond oxygens at 180 degrees, they cancel out. And boron trichloride, that boron has nothing but chlorine around it. That's going to be a nonpolar molecule as well. This picture shows CH4 methane being replaced by 1 chlorine at a time until you get to the far right, which is carbon tetrachloride, CCl4. And notice what happens to the polarity. So on the far left-hand side, CH4, everything, all the carbon is completely surrounded by hydrogens. So everything around the carbon is the same. This one's going to be nonpolar, all right? And on the far right, even though chlorine is pretty electronegative and it pulls electrons pretty strong, everything around the carbon is the same, all chlorines. It's also nonpolar. But if you start now back on the left again, CH4, you replace one of the carbons with a chlorine. Hey, now we've got an asymmetric orientation of atoms. That carbon has 3 hydrogens and 1 chlorine. Everything is not the same. Polar. If you have a dipole moment, that means it's polar. If you replace a second hydrogen with a chlorine, still asymmetric, polar. Replace a third hydrogen with a chlorine, now again asymmetric because 1 hydrogen and 3 chlorines, nothing's the same, polar. But again, you had every position with hydrogen you replace with a chlorine, that's going to have a symmetric environment once again, nonpolar. So the far extremes are nonpolar, but everything in the middle is polar. It shows the importance of knowing if something is symmetric or asymmetric. All of these molecules shown are actually symmetric, and it's something we'll talk about more in future lectures. But if you have like a central point where everything is the same around it, it's going to be nonpolar. So as an example, this compound ethene in the upper left, you can have like a dot right there in the middle, and everything on the left and the right is the same, and this is a flat molecule. That's going to be nonpolar. And acetylene, which has a triple bond, you can do the same thing. Everything to the left and the right of that molecule will be the same, nonpolar. Now with this molecule, you have to be a little bit more creative, but if you put a dot in the exact middle, everything around that dot is the same, like a CH at all different places, so that's what makes it nonpolar, etc., etc. So there's a lot of nonpolar molecules out there, but again, there's a lot more polar molecules too, so usually if you just guess polar, you'll be okay. But again, try to think about it in terms of symmetry if you can.